Section: Introduction. In this section, we will discuss how language models work. Language models predict the likelihood of the next word in a sentence based on the words that came before it. This prediction helps generate text. But can we use this prediction to figure out the original input sentence? Usually, this question doesn't make sense because we already know the input. However, with the rise of language models offered as a service, users may not have access to the full input sentence. In such cases, it can be useful for users to know the input and for the service provider to keep it private. Some methods, known as jailbreaking, try to use the model's text generation to uncover the input. We define this problem as prompt reconstruction, where we try to recover the original input based on the model's next word predictions. Interestingly, research in computer vision has shown that predictions from image classifiers contain a lot of detail. This suggests that language models might also retain similar information. We introduce a method that predicts inputs by breaking down the probability distribution into a sequence that a pre-trained language model can process effectively. Our method demonstrates that language model predictions can mostly be reversed. In many cases, we can retrieve very similar or even exact original inputs. We also explore different ways to recover the input prompt in real-world scenarios, such as full next word probabilities, top choices, probabilities per word on request, and random sampling. Even when we can only see the model's text output, without probabilities, we can still gather enough information to reconstruct the input. Our findings reveal that systems offering text-only access to a language model leak information about their prompts. With sufficient queries, we can extract next word probabilities at a specific position to reconstruct the input. Unlike text-based jailbreaking methods, our approach of dense distribution inversion is less affected by post-pre-training reinforcement learning techniques. We show that our inversion techniques work across similar models and are not impacted by the size of the language model. Moving on to related work, previous studies in computer vision have shown that inputs can be roughly reconstructed from image classifier predictions. Some research has also focused on inverting representations in natural language processing. Our work is the first to directly invert language models based on their probability outputs. Model inversion aims to create an input that produces a given output from a model. This technique has been applied to various types of classifiers, including neural networks. Model inversion can sometimes help recover training data, as demonstrated in face recognition systems. Our work focuses on prompt inversion, a more complex task involving high-dimensional inputs from language models. Instead of recovering training data, we aim to uncover the specific input prompt while filtering out training-related information. As language models become more valuable, they are increasingly protected. Research on model stealing explores replicating models through API queries. While model stealing has been demonstrated in various NLP tasks, our focus is on uncovering hidden prompts from third-party model outputs, rather than reconstructing model weights. Lastly, we delve into prompt reconstruction. Language models provide the probability of the next word given the preceding words. These models typically have large vocabularies, containing tens or hundreds of thousands of words. Section Summary. In this section, we explore the concept of prompt reconstruction in language models, which involves recovering the input prompt based on the next token probabilities generated by the model. We propose a novel architecture that effectively predicts prompts by unrolling the distribution vector into a sequence, demonstrating that language model predictions can be mostly inverted to recover similar or exact input prompts. Our study reveals that even with limited access to model outputs, such as text-only information, it is possible to reconstruct the prompt by extracting next token probabilities, showcasing the potential information leakage in systems offering text-based access to language models. Section: Logits contain residual information. In this section, we conducted a simple experiment to show how much information the language model, LM, logits can reveal about the input. We took 100 text inputs from Wikipedia and replaced a word in the first sentence with a synonym. We denoted the synonym of word X_S as #x_s. To measure the difference in the LM output between the original sequence, with x_s, and the new sequence, with #x_s, we calculated the KL divergence between the probability outputs of P for both sequences and the bit-level Hamming distance between the two distributions represented at 16-bit precision. We then plotted these values relative to the position of the synonym swap in a figure. If LMs didn't contain residual information about previous words, we would expect the bit-level distance to decrease to 0 as we moved away from the swap position. However, we observed that bits remained, indicating that the LM not only predicted the next token but also retained information about the preceding tokens x_1, x_t. The KL divergence tended to decrease to 0, focusing on the most likely tokens, while valuable information remained in the less probable tokens. Next, we explored the task of reconstructing the prompt. Given a probability vector, we aimed to generate the prompt that led to these probabilities for the next token. We wanted to learn to reverse this process using samples consisting of text prefixes and their corresponding next token probability vectors. Additionally, we considered predicting the prompt directly from the LM output as an alternative to inverting the probability vector. For instance, from the model output, Bogotá, we could predict the input, what is the capital of Colombia? We believed that a single logit vector contained more detailed prompt information than a single sequence sampled from the argmax of these vectors. This scenario was further examined in our sample inverter baseline as described in the experimental design section. We created a metadataset called Instructions2M, comprising 2.33 million instructions with user and system prompts for various problems. This dataset included prompts from different sources such as supernatural instructions, self-instruct, alpaca, Dolly, share GPT, unnatural instructions, chatbot arena, stable diffusion dataset, wizard LM instructions, GP teacher, T0, and LaMini instruction. We also gathered out-of-domain prompts to evaluate the model's ability to generalize across different topics. Our study was motivated by the widespread use of language models as a service. We assumed that an unknown prefix sequence, known as the prompt, was added to the user input in these scenarios. We considered different levels of model access, ranging from full distributional access to text output access only, without access to the model weights or activations. Our proposed method involved training a conditional language model to map next token probabilities back to tokens P, x_1, T, V. We used a pre-trained transformer language model and trained it on samples from the unconditional model. By leveraging cross-attention in an encoder-decoder transformer, we conditioned the model on the next token vector. To adapt the probability vector, V, for input to the language encoder, we transformed it into a sequence of pseudo-embeddings, C_I in R_D. This allowed us to condition the transformer outputs on the complete probability vector, V, where x** represented the predicted inversion, D denoted the embedding dimension, and V was padded with zeros at the final position. In our experiments, we used vert V, vert equals 32,000 and D equals 768, resulting in a fixed-length input sequence of 42 words. Section Summary. In this section, we demonstrate that language model logits contain residual information by swapping synonyms in text inputs and measuring the change in model output using KL divergence and Hamming distance. We explore inverting the process by predicting the prompt from the output probabilities and construct a metadata set of instructions for various problems to test model generalization. Our proposed method involves learning a conditional language model to map next token probabilities back to tokens using a pre-trained transformer model and conditioning on the next token vector through cross-attention in an encoder-decoder transformer. Section: Extracting logits via API. In this section, we discuss how we can extract logits via API calls. Many language model platforms only provide limited information through their API, such as samples or the TOP5 log probabilities, rather than the full output probabilities. To address this limitation, we propose a method to extract next token probabilities from APIs that do not immediately provide the complete probability distribution. We leverage the ability of API services to adjust the distribution by adding a logit bias and setting the temperature parameter to 0 to obtain the argmax of the distribution. We introduce an algorithm that uses binary search to find the logit bias for each word, allowing us to recover the probability of each token by determining the difference with the most likely word. This binary search approach can be independently applied to each word, enabling parallelization and requiring only one logit bias at a time. By applying this method to every word in the vocabulary, we can reconstruct the full probability distribution using softmax on the logits. The number of queries needed to determine the distribution is proportional to the vocabulary size multiplied by the number of bits required for the desired precision. For our experimental setup, we train models to invert the distribution of Llama 2 and Llama 2 Chat, which are top-performing open-source language models. During the distribution extraction experiments, we set the temperature to 0 and provide a single logit bias argument. We use the T5 base model as our encoder-decoder backbone and train the inversion models for 100 epochs with the Atom optimizer. We evaluate the models using various metrics such as F1 score, blue score, exact match, and cosine similarity between original and recovered text embeddings. Since there are no prior baselines for inverting text directly from language model probabilities, we develop several baselines including jailbreak strings, GPT-4 few-shot, and a sample inverter. These baselines help us assess the performance of our inversion models in comparison to alternative approaches. Section Summary. In this section, we propose a method to extract next token probabilities from language model APIs that do not provide the full probability distribution. By leveraging the ability to adjust logit biases and set temperature parameters to 0, we can recover the probabilities using binary search for each word independently, allowing for parallelization. We conduct experiments using an inversion model trained on Llama 2 distributions, achieving prompt reconstruction metrics such as F1 score, blue score, exact match, and cosine similarity, with no prior baselines available for comparison. Section: Results. In this section, we present the main results of our experiments on reversing prompts from the instructions 2M test set using both a raw LLM and RLHF chat variant. We discovered that our method can achieve a high blue score with the true prompts and produce reasonably high exact match reproductions. Our approach outperforms few-shot prompting methods, even when compared to GPT-4. Another trained approach called sample inverter has a decent blue score but 0 exact recoveries. This failure suggests that we can extract more useful information about the prompt from the logit vector than from just the argmax outputs. When compared to manually written jailbreak strings, our approach performs significantly better than average and is comparable to the Oracle jailbreak method. Interestingly, while the best jailbreak method works well on the raw LM, none of the jailbreak approaches are effective on the RLHF chat version. We also observed that our method works slightly better on the non-chat model, indicating that the RLHF training procedure for the chat model may reduce the available information from the next token probabilities. When using prompts that are significantly different from the training distribution in terms of length and content, our model performs significantly better than few-shot and jailbreaking methods on the RLHF model. Additionally, jailbreak strings are notably ineffective on the Anthropic HH dataset with toxic content, suggesting that the chat model may not follow user requests when toxic content is present. We also examined our ability to recover the next token probability distribution using an API-based logits extraction method. Our deterministic algorithm extracts useful logits with fewer queries compared to a naive Monte Carlo sample baseline. This aligns with our hypothesis that valuable information lies in the probabilities of very unlikely words. Furthermore, we investigated the transferability of inversions to models of different sizes and found that inversions transfer reasonably well, especially between non-RLHF models. We speculate that further fine-tuning may be necessary for models to adapt to different sizes. To understand the dependence of inversion results on language model size, we inverted different sizes of GPT-2 and found that the reconstructions perform similarly regardless of the model size. This contrasts with findings in CNNs, where more layers of computation make inversion more challenging. Lastly, we explored defenses against prompt inversion by adding noise to the language model output distribution through sampling mechanisms. We observed a trade-off between language model fidelity and inversion performance, with certain sampling strategies performing better than others.